Welcome to day 6. Today we're going to use the first and second derivative to do tests on functions to determine where the function is increasing or decreasing or concave up or concave down. So if you remember from last class, we talked about the first derivative. I determined where the first derivative was either positive, negative, or 0 depending on what was going on in the graph. F prime was equal to 0. We said were called critical points. And for what we are going to be working on, f prime was equal to 0 because these were local mins or local maxes. Okay, they don't have to be. We might have an example where they don't happen, but for the most part, when f prime is equal to 0, that means the slope of that graph is equal to 0. That should be a local min or local max. We also talked about when f prime was positive, that our function should be increasing. And then when f prime is negative, our function should be decreasing because f prime being positive means it has a positive slope, and f prime being negative means it has a negative slope. And then we really also talked about the second derivative describes concavity. So when f double prime is equal to 0, that's going to be our reflection point. It's where it changes concavity. F double prime is positive, the function is concave up. And if f double prime is negative, the function is concave down. So last class we looked at graphs and we put down positive, negative, or 0 for f prime or f double prime. Today we're going to look at equations of functions and we're going to determine where things are increasing and decreasing or concave up, concave down without looking at any graph. So what we're going to do today is called the first and second derivative test. We're going to use the first derivative and set it equal to 0 to find the critical points. Okay, I may have to factor, but these critical points are where we have local mins and maxes is really where a graph could change from increasing to decreasing. If you go from increasing to decreasing, you have to hit 0 at some point, or vice versa. We're going to plot these numbers on a number line, and we're going to determine where f prime is positive or negative. Well, wherever f prime is positive or negative, that will tell me where the function is increasing or decreasing. Okay, this whole number line business is going back exactly to what we did in Unit 2 when we did polynomials, and we just made a number line instead of drawing a two-dimensional graph. Then we're going to do the second derivative, set it equal to 0, and these will be our inflection points. And then after that, we're going to plot these inflection points on the number line, and we're going to determine where f double prime is positive or negative, and that's going to tell me where the function is either concave up or concave down. Okay, it's not really that hard. We're going to take the derivative using our power rule, our shortcut rule, and we're going to set it equal to 0, and we're going to solve, and we're going to find critical points and inflection points, and kind of set our number lines with the plus and minus signs like we did earlier this year. So let's do an example. Here's my function g of x. I'm going to find the derivative, so g prime of x, using my power rule, is 3x squared minus 4x minus 4. And I'm going to set this equal to 0. I think I need to do some factoring. 3x and x. And to get 4, I mean, it's either 4 and 1 and 2 or 2. I'm going to do plus 2 here, minus 2 here. And if I check it, I notice I get minus 6x plus 2x. I get my negative 4x that I want. Now I'm going to solve for it. I get 3x plus 2 is equal to 0. X minus 2 is equal to 0. So I get x equals minus 2 over 3. I get x equals positive 2. And these are my critical points. This is when the derivative is equal to 0. So now I'm going to plot these critical points on a number line. So this number line represents g prime, not the original function g prime. And my two critical points are negative 2/3 and positive 2. These are the zeros. And now I'm going to put in the plus and minus signs because I have to determine if things are increasing or decreasing. Well, I know the leading term of g prime, not g, of g prime is 3x squared. So that means this goes positive here on the right side. There is no bouncers here. Negative in the middle. And then positive over here on the left side. So what does that mean for a function? Well, obviously the positive is where the original function is increasing, the negative is where it's decreasing, and the positive again is where it's increasing. So I can answer the question. It is increasing from negative infinity to negative 2/3 in union with 2 to infinity, and it is decreasing from negative 2/3 to 2. And I'll put that in a nice little box. Okay, so I don't even have to look at a graph. I know where things are increasing and decreasing. So now I have to figure out where I have local mins and maxes, if I do have local mins and maxes. Well, if you have a local max, that is because you're going from an increasing function to a decreasing function. So a graph that looks like this would have a local max. And the reason why it has a local max is because G prime, which is purple, G prime, or the derivative, goes from positive to 0 to negative. So if you ever see that you have your derivative goes from positive 0 to negative, it is a local max. Let's see, do I have a positive 0 negative anywhere? I do, right here. I have a positive 0 negative for my derivative, so negative 2/3 is a max. Conversely, if it goes decreasing to increasing, that means the graph looks like this. This is a local min because your derivative is going negative 0 positive. And I have to notice, do I see anywhere on this? Well, let's see. It goes negative 0 positive, so x equals 2 is a local min. So for part C, it says determine the local min and local max values. Well, I have a max at x equals negative 2/3. I have a min as x equals 2 because there's a max because G prime goes positive 0 negative, and there's a local min because G prime goes negative 0 positive. Okay? So only way you could have a min or a max is that we have to change signs on our derivative. If you go positive 0 positive, that's not going to be a min or max because it's increasing 0 increasing. That's not changing direction. Now the second part that I'm going to have to do is figure out concavity, and I have to do the inflection point, so I have to figure out the second derivative. I just have to go back up here and take this first derivative that I have here in blue, and I'm going to copy it down, and I'm going to take a second derivative. So here's that first derivative and the second derivative. Just take another derivative, 6x minus 4. I'm going to set it equal to 0, and I'm going to add 4 divided by 6, and I'm going to reduce my fraction. Always reduce fractions. And I get x equals 2/3 as the inflection point. So this is going to be key to me. So I'm going to put this on the number line, and this is going to be a G double prime number line. That's right here, 2/3. And that's where my 0 is at on G double prime. Again, I should pay attention to the leading term. Well, the leading term of G double prime, not the original function, not prime, is 6x. That means over here I have a positive, and over here I have a 0 and I have a negative because there's no bouncers. So the negative is where it's concave down, and the positive is when it's concave up. So if I want to write everything where it's concave up and concave down, it is concave up from 2/3 to infinity. It is concave down from negative infinity to 2/3. And now if I wanted to, I can plot basically a sketch of this graph with some key details. Well, my sketch of g of x, if I go back to the original g of x, it is x cubed function with all those other terms. So it's going to be like this, a snake. Positive x cubed always going to look like this. Well, let's see. I think we determined that we had a max here at x equals negative 2/3. I had a min here at x equals 2. And then I had right here in the middle an inflection point at x equals positive 2/3. And we can match what we did before. It is increasing from negative infinity to negative 2/3 and from 2 to infinity. It is decreasing from negative 2/3 to 2. It is concave down from negative infinity to 2/3. It is concave up from 2/3 to infinity. It all matches. Okay, another example. We have h of x equals negative 2x cubed plus 9x squared plus 168x minus 3. I'm going to take its, to find its critical points, I have to take its derivative and set it equal to 0. So h prime of x is equal to negative 6x squared plus 18x plus 168. I'm going to set it equal to 0. I also see that I don't like really working with these big numbers. I can divide everything by negative 6. I get x squared minus 3x minus 28. Set that equal to 0. Much easier to factor. X and x. I would say minus 7 plus 4 will give me my negative 28 and my negative 3 in the middle. And when I solve for x, I get x equal to negative 4 and positive 7. And these are my critical points. I'm going to put these critical points on this number line, negative 4 and 7. These are my zeros for my derivative. Now, my leading term for my derivative is not x squared. It is actually negative 6x squared. If you pay attention to the original problem, that means the right side goes negative, no bouncers, middle goes positive, the left side goes negative. What does that mean? This is decreasing, this is increasing, this is decreasing. So it is increasing from negative 4 to 7, and it is decreasing from negative infinity to negative 4, union 7 to infinity. Next, I need to find any mins and maxes. Well, for here, this part goes negative 0 positive, and negative 0 positive is going to go down and then up. That's a min. And then this part is positive 0 negative, and that means it goes increasing and decreasing. That means this is a max. So I have a minimum at x equals negative 4. I have a maximum at x equals 7. And if you want to state why, because I think it's good that you should, that's because h prime for the minimum goes negative 0 positive, or the function goes decreasing to increasing, and it has a max at x equals 7 because h prime goes positive 0 negative, or it goes increasing to decreasing. So to find the inflection point, I have to do h double prime is equal to 0. That means I have to go back and take my derivative here in blue, not the one I did in pink, that was cleaned up, that was factoring, but the one in blue, because that's really the derivative, and take the second derivative. So here's my derivative. So the second derivative will be negative 12x plus 18. Set that equal to 0. Let's see, subtract the 18, divide by negative 12, clean up my fraction. I get x is equal to 3 over 2. This is my inflection point. This is where the graph is going to change concavity. So now this is where I'm going to do my h double prime number line. The only number I have on this one is 3 over 2. That's my 0 value. I have to pay attention. The leading term for the second derivative is negative 12x. That means this right side is negative, and then after the 0 it's positive. So this part is concave up, this part is concave down. I can write down my concave up is from negative infinity to 3 over 2, And my concave down is from 3 over 2 to infinity.